Three-phase power and its effect on energy savings depend heavily on the type of electrical load it is serving. Considering linear circuits, such as electric heat, three-phase power does not inherently offer any energy savings. Electric heat is functioned by converting electrical energy directly into heat. The amount of power they consume is primarily dictated by the resistance of the heating element and the voltage applied to it. While three-phase power introduces a different voltage waveform and generally provides a high current capacity, it does not fundamentally alter the energy consumption characteristics of the heating element itself. In contrast, when dealing with nonlinear circuits, specifically motors, three-phase power presents opportunities for energy conservation. Motors, by nature, are inductive loads. This means they introduce a lagging power factor, where the current waveform trails behind the voltage waveform. This phase difference leads to power losses within the system. Three-phase power, however, offers a solution. It supplies three distinct sets of voltage waveforms. These waveforms can be strategically utilized to counteract or cancel out the lagging power factor induced by the motor. By mitigating the lagging power factor, the overall power factor of the system is improved. This improvement directly translates to a reduction in power losses. The extent of energy savings achievable through this method is contingent on several factors. These factors include the specific characteristics of the motor in question and its prevailing operating conditions. However, in applications characterized by substantial motor loads, the potential for significant energy savings is definitely there. To summarize, three-phase power does not yield energy savings when used with linear circuits like electric heat. Conversely, it can be an effective means of saving energy in nonlinear circuits, such as those powering motors, by enhancing the power factor and consequently minimizing power losses. Electrical circuits can be categorized into two main types: linear and nonlinear. Linear circuits are those in which the relationship between voltage and current is directly proportional, meaning that if you double the voltage, the current also doubles. Examples of linear circuits include resistors, capacitors, and inductors when they are operating within their linear range. Nonlinear circuits, on the other hand, do not have this direct proportional relationship. The current and voltage relationship is more complex and can change depending on the conditions. Examples of nonlinear circuits include diodes, transistors, and motors. Electric heat is a purely resistive load, which means it is a linear circuit. When voltage is applied to a resistive heating element, the current flow is directly proportional to the voltage, as described by Ohm's law: voltage equals current times resistance. The power consumed by the heating element is calculated as power equals voltage times current, or power equals current squared times resistance, or power equals voltage squared divided by resistance. Regardless of whether the power source is single-phase or three-phase, the total power consumed by the heating element for a given resistance and voltage will be the same. Therefore, using three-phase power for electric heat does not result in any energy savings. Motors are inductive loads, and their behavior is more complex than that of resistive loads. When an alternating current voltage is applied to a motor, the current lags behind the voltage due to the motor's inductance. This lagging current results in a power factor that is less than 1.0. The power factor is a measure of how effectively the electrical power is being used. A power factor of 1.0 indicates that all of the power is being used to do work, while a power factor less than 1.0 indicates that some of the power is being wasted. The wasted power is called reactive power, and it circulates between the source and the load without doing any useful work. Three-phase power can improve the power factor of motors because it provides three balanced voltage waveforms that are 120 electrical degrees apart. This balanced voltage supply helps to smooth out the current flow in the motor, reducing the amount of reactive power and improving the power factor. A high power factor means that less current is required to deliver the same amount of real power to the motor. This can result in energy savings, reduced heating in the motor and wiring, and improved voltage regulation. The amount of energy savings that can be achieved by using three-phase power for motors depends on several factors, including the motor's size, load, and operating conditions. However, in general, Three-phase power can provide significant energy savings for motors, especially in large industrial applications. Improving power factor in electrical systems offers several key benefits. Firstly, it reduces energy costs by minimizing the amount of reactive power that the utility company charges for. Secondly, it increases the system's capacity by freeing up distribution infrastructure, allowing more real power to be delivered. Thirdly, it improves voltage regulation, leading to more stable and efficient operation of equipment. Fourthly, it reduces losses in cables and transformers, leading to increased overall system efficiency. Fifthly, it extends the life of electrical equipment by reducing stress on insulation and conductors. It's important to note that the actual savings depend on several factors, including the existing power factor, the load profile, and the cost of electricity. Power factor correction can be implemented using various methods, such as installing capacitors or using active power factor correction devices. The choice of method depends on the specific application and the desired level of correction. Motors are not perfectly linear because of factors like saturation in the iron core, which means the relationship between voltage and current is not strictly proportional over the entire operating range. However, for the purpose of understanding the difference between electric heating and motor loads, motors are considered a nonlinear load due to the inductive effects which contribute significantly to the phase shift between voltage and current. The design and operation of electric motors are rooted in fundamental electromagnetic principles. Motors convert electrical energy into mechanical energy through the interaction of magnetic fields. This process involves several key aspects. Firstly, a magnetic field is created by passing current through coils of wire, typically wound around an iron core. The strength and direction of this magnetic field can be controlled by varying the current. Secondly, when a current-carrying conductor is placed within a magnetic field, it experiences a force. The magnitude and direction of this force are determined by the strength of the magnetic field, the magnitude of the current, and the orientation of the conductor relative to the field. Thirdly, in a motor, conductors are arranged in a specific configuration, often in the form of a rotating armature, to maximize the force produced. The magnetic fields are carefully designed to interact in a way that generates continuous rotational motion. Fourthly, the motor's speed and torque are controlled by adjusting the voltage and current supplied to the motor. Higher voltage and current typically result in higher speed and torque. Fifthly, factors such as the number of poles in the motor, the winding configuration, and the magnetic properties of the materials used all influence the motor's performance characteristics. Different types of motors, such as induction motors, synchronous motors, and direct current motors, employ different techniques to achieve these principles. Induction motors rely on electromagnetic induction between the stator and rotor, while synchronous motors use synchronized magnetic fields. Direct current motors use commutators to reverse the current direction in the armature, enabling continuous rotation. Electric heating is a fundamental process that relies on the principle of converting electrical energy into thermal energy. This conversion is achieved through the use of resistive heating elements, which are materials specifically designed to impede the flow of electric current. When an electric current passes through a resistive heating element, the electrons within the material collide with the atoms, causing them to vibrate and generate heat. The amount of heat generated is directly proportional to the resistance of the material and the square of the current passing through it, as described by Joule's first law of heating. The key aspects involved in electric heating include, firstly, resistive heating elements are made from materials that offer significant electrical resistance, such as nichrome, xanthal, or tungsten. These materials are chosen for their ability to withstand high temperatures and resist oxidation. Secondly, the heating element is designed to have a specific shape and size to achieve the desired heat output and distribution. The design also considers factors such as heat transfer and thermal conductivity. Thirdly, the electric current is controlled by a thermostat or other control system to maintain a desired temperature. The control system regulates the amount of current flowing through the heating element. Fourthly, heat is transferred from the heating element to the surrounding environment through various mechanisms, including conduction, convection, and radiation. Conduction involves heat transfer through direct contact, convection involves heat transfer through the movement of fluids, and radiation involves heat transfer through electromagnetic waves. Fifthly, different types of electric heating systems, such as resistance heating, induction heating, and infrared heating, employ different techniques to generate and transfer heat. Resistance heating uses resistive heating elements, induction heating uses electromagnetic induction, and infrared heating uses infrared radiation. The efficiency of electric heating depends on factors such as the type of heating element, the insulation of the heated space, and the control system used. Proper insulation and efficient control systems can help minimize heat loss and maximize energy efficiency. The NEC, or National Electrical Code, is a comprehensive set of standards and guidelines for safe electrical installations. Article 220.84 addresses optional method calculations for additional loads in existing dwellings. This section provides guidance on calculating the allowable ampacity for adding new electrical loads to an existing residential service. The NEC is updated every 3 years to incorporate new technologies and address emerging safety concerns. Adhering to the NEC is crucial for ensuring the safety of electrical systems and preventing hazards such as fires and electric shocks. Compliance with the NEC is often mandated by local building codes and regulations. Licensed electricians are trained to interpret and apply the NEC in their work. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Understanding the NEC is essential for anyone involved in electrical work, from homeowners to professional electricians. The NEC provides detailed tables and examples to assist in calculating electrical loads and determining appropriate wiring sizes. The NEC also includes requirements for labeling and marking electrical equipment to ensure proper identification and safety. The NEC emphasizes the importance of using listed or certified electrical equipment that has been tested and approved by recognized testing laboratories. The NEC is not a substitute for proper training and experience in electrical work. It is intended to supplement, not replace, sound engineering judgment and safe work practices. The NEC is a living document that is constantly evolving to keep pace with advancements in electrical technology and safety standards. The NEC is available for purchase from the National Fire Protection Association, NFPA, and other distributors. Many jurisdictions also make the NEC available online for reference. Staying up to date with the latest edition of the NEC is essential for ensuring compliance and maintaining electrical safety. The NEC is a valuable resource for anyone involved in electrical work, providing guidance on safe and reliable electrical installations.